Hello everyone! Welcome to the second video of our Fidelity for Hydraulic Turbines series. Today I'm going to share with you how to use Fidelity AutoMesh for a hydraulic turbine project. We will combine an AutoGrid structured algorithm to mesh the guide vanes and runner with Express volume to surface unstructured mesh algorithm to mesh the draft tube. As in the last video, we will start by opening a turbo template and import the same geometry. We're also going to create a turbo configuration that will contain a guide vane and runner. The turbo machinery tree on the left allows to simplify the project structure so that we can focus on the assemblies and boundaries that we need, while at the same time keeping the original CAD structure on the right. We see that we only have one row, so we'll add another one. Rename both of them and make sure that only the runner is rotating. Now we need to link this turbo configuration to the geometry on the right. So we're going to isolate our hub and change our selection mode to surface and curve mode to select both curves that comprise the hub. In order to simplify the process, we will create a profile that will contain both hub curves as one geometry entity. And then we can proceed to link it. Finally, if the link is successful, we will see the half curve in the meridional view. We also need to do the same with the shroud. In this case, there is only one curve, so we can skip the create profile part and we just need to make sure that it has the correct orientation. It is correct, so we can link it to our turbo configuration. Next step is to link the blades for each row. Since we have the full 360 degrees geometry, but the structure algorithm only requires to mesh one flow passage, we only need to do this for one of the blades of the CAD tree. We select the pressure side and suction side to link with the main blade on the turbo machinery tree. We do the same for the runner. Before we continue, it is good practice to perform a geometry check. We do this for the guide vane. Oh, we get a warning that the trailing edge has not been defined, but that's fine because it will be computed in the next step. Now we do this for the runner. We get an error this time, because the default tolerance is not enough. So let's slightly increase that and try again. Now we only get the warning, so we can continue and compute the trailing edge and leading edge. Now we will define the periodicity. For the guide vane row, we have 24 blades, and for the runner row, we have 13 blades. Finally, let's double check that the blades geometries are correct after generating the trailing edges. Alright, now we need to create another assembly to link the draft tube. For this assembly, we need to add 5 different boundaries, so we can either set mesh parameters independently or different boundary conditions. We will have one for the outlet, one for the rotor stator, one for the hub tip, which rotates, one for the cone and elbow, and finally, one for the diffuser. We need to link them to the corresponding patches on the CAD tree. The procedure is very similar to the one we used for the blades. We make sure to link outlet hub tip. Cone and elbow together. Note that part of the shroud selection is actually the cone, so we need to add it by pressing Ctrl key. Diffuser. The only patch that we left is the rotor stator, because in fact there is no such rotor stator surface in the CAD that we imported. However, this is not a problem, because Fidelity will automatically generate it from the guidevane and runner mesh setup. Next step, we're going to generate a cylinder that we will use for the volume refinement of our draft tube mesh. For it to be centered in the cone, we make sure to select the shroud selection on the CAD tree, and Fidelity will use its bounding box to create it. We extend it and increase its radius so that it covers the whole cone and most of the elbow. Alright, we have finished doing all the work at geometry context. So we will create two mesh setups, one for the guidevane and runner, and one for the draft tube. And then we move on to domain context. On the left, we can see the different domains that have been automatically generated from the last action. For the draft tube, we will be using Express and Structured Mesh Engine. In fact, today, we will be using its volume to surface algorithm, which requires to define a seed point that should be always inside the domain, since the mesh will grow from it. After that, we're going to create the connections between the domains. We see that Fidelity has automatically generated the rotor stator between the guidevane and the runner. But we need to create a new rotor stator between the runner and the draft tube. For doing so, select the runner outlet, add it on the left side, select the rotor stator and linked patch and add it to the right side. After making sure that all the boundary conditions are correctly set, we can proceed to mesh context. We will focus first on the turbo configuration, for which we will use AutoGrid Mesh Engine, which is a structured algorithm. The first thing to do is to move the inlet closer to the guidevane and set it to 0.27 meters. Next, the outlet, we want it to be curvilinear. We spend a bit of time until we are happy with its shape, but know that it's also possible to import a predefined curve directly. Now, we will use the row wizard to automatically set the grid parameters. Row type, Francis turbine. Periodicity has already been set, flow path number 49. And cell width, we will set to 2e-5 meters. After applying the wizard, we can see in the blade to blade view that it is too fine. So let's reduce the grid refinement level to -9 and try again. Okay, this is much more appropriate. We also do the same for the runner, and after we are satisfied, we can generate a 3D mesh using 4 cores. After just 1 minute, the mesh is generated, and we can check its quality and performance values in a summarized table. Now we can move on and generate the draft tube mesh. But before that, we need to generate the rotor stator surface. So we click in Prepare Mesh Connection. And now we can see in the 3D view that the surface has been created. Let's now unload the mesh setup from Turbo Configuration and enlarge the 3D view to focus on the draft of mesh. The first thing we'll do is to add the refinement cylinder that we created in geometry context. We will add a refinement level of 2. We set the initial cell size depending on how fine we want the bulk of our mesh to be. We also set local refinement. For the hub tip selection, we're going to set 4 refinement levels. Thanks to Fidelity's mesh preview feature, we are sure that this is enough to capture this area before generating the mesh. Let's also define the viscous layers. We will do it for all the wall patches at the same time. First layer thickness, number of layers, and stretching ratio. Let's click now on Diffuser and modify the first layer thickness to 1e-4, so that we can reduce the number of layers to 12, and at the same time ensuring a good transition with the Illyrian mesh. For the hub tip, we will maintain the same first layer thickness, but reduce the number of layers to 13, since it is more refined. Note that if we select 2 patches with different parameters at the same time, Fidelity will make them stand out for us in yellow. That's all. We are now set to generate the mesh. We will run it with 12 cores to fully harness the code parallelization. After just a few minutes, the mesh generation has finished, and we can check the overall quality of the mesh as before. We see that we have 1.8 million cells. Maximum skewness is about 0.66, and it generated in 5 minutes and 50 seconds. If we want to see the inside, we can create a cutting plane. Let's set it to be perpendicular to X direction and click to show the wireframe. For Fidelity to process, we need to start the post-processing of the mesh. We can move the plane if we want to, or change the intersection mode to see the full cells. We may also create contours with different quality parameters to find the regions with more room of improvement. Alright, so now that we have both meshes for Draftive and Guidevine and Runner, we can proceed to the simulation context. But we'll do this in our next video, in which we will run a simulation with our coupled pressure-based solver and also show you how to do the post-processing. Thank you for watching.